Okay, in this lecture, we'll be discussing moments and LP spaces. Let X be a random variable mapping from omega to R defined on a probability space. Omega script Fp with a distribution function Fx from R to closed interval 0.1. Let's first consider an example, the absolute value function. For the function absolute value of dot mapping from R to R plus, we can look at the inverse image of half open sets minus infinity x for any real x. Let's call this a g of x, which is g inverse of minus infinity x. It follows that a g of x is the empty set which is in script b of R if x is less than 0, and a g of x is the closed interval minus xx which is also in script b of R if x is in R plus non-negative reals. Since g inverse of minus infinity x is in script b of R for all x, it follows that the absolute value function is a Borel measurable function. Now, a lemma regarding moments. If the expectation of the absolute value of x, e of absolute x, expectation of absolute x is finite, then the expectation of x, e of x, expectation of x exists and is also finite. For the proof, first, the absolute value function mapping from R to R is a Borel measurable function, as we just discussed. Hence, absolute x is itself a random variable. Second, absolute x is always greater than or equal to 0. Therefore, its expectation E of absolute x, expectation of absolute x always exists, though it could be infinity. Third, if E of absolute x, expectation of absolute x is finite, this means that E of x plus expectation of x plus and E of x minus expectation of x minus are both finite, since absolute x equals x plus x minus. Consequently, E of x, expectation of x, which is defined as E of x plus minus E of x minus, expectation of x plus minus expectation of x minus, is also finite. As a corollary, let G from R to R be a Borel measurable function. If the expectation of the absolute value of G of x, E of absolute G of x is finite, then the expectation of G of x, E of G of x exists and is finite. Here's an exercise for you. Consider polynomial functions. For any natural number k, define functions gk from R to R such that gek maps x to the power k. Show that gk is a Borel measurable function for all k and n. This brings us to the definition of moments. We define the kth moment of a random variable x as mk, which is E of gk of x, or simply expectation of x to the k. The first moment, E of x expectation x, is specifically called the mean of the random variable. Some reminders regarding moments. If expectation of absolute x to the k is finite, then the kth moment mk exists and is finite. If the probability p that absolute x is less than or equal to 1 is 1, meaning x is bounded by -1 and 1 almost surely, then the probability p that absolute x to the k is less than or equal to 1 is also 1. By the monotonicity of expectations, expectation of absolute x to the k will be less than or equal to 1. Consequently, the moments mk exist and are finite for all natural numbers, k in this case. Now let's introduce LP spaces. First, a definition of a vector space. A vector space over a field script F is denoted by a set V. It must satisfy two main sets of properties. A, vector addition, a function plus from V cross V to V, must satisfy associativity and commutativity, and there must be an identity element 0 vector and an additive inverse element for each vector V in V. B, scalar multiplication, a function dot from script F cross V to V must satisfy compatibility with field multiplication, distributivity with respect to both vector addition and field addition, and there must be an identity element for scalar multiplication, usually the scalar 1. As a reminder, the set of random variables defined on a common probability space forms a vector space over the real numbers. Let's call this V. We can verify associativity and commutativity of addition for random variables. The constant function 0 acts as the identity random variable, the 0 vector, and minus x serves as the additive inverse for a random variable x. Similarly, properties like compatibility of scalar multiplication, existence of a unit scalar, and distributivity all hold for random variables. Next, let's define a norm. For a vector space V over a field script F, a norm on this vector space is a map F from V to the non-negative reals R plus that satisfies three properties. First, homogeneity. F of a times V equals absolute value of A times F of V. For all scalars A in script F and all vectors V in V. Second, subadditivity, also known as the triangle inequality. F of V plus W is less than or equal to F of V plus F of W for all V, W in V. And third, point separating or positive definiteness. F of V is greater than or equal to 0 for all V in V, and Fv equals 0 if and only if V is the 0 vector. The slide only states Fv greater than or equal to 0, but the IFF 0 vector part is usually included for a norm. Now we can define LP spaces. For a probability space omega script F P, and for P greater than or equal to 1, we define the set LP as the set of all random variables x in our vector space V such that E of absolute x to the P all raised to the power 1 over P. Expectation of absolute x to the P to the 1 by P is less than infinity. This LP is a vector space. We also define a function norm sub P, which maps from LP to R plus. Norm sub P of x, also written norm x sub P, is defined as of absolute x to the P raised to the power 1 over P. Expectation of absolute x to the P to the 1 by P for any x in LP and for real P greater than or equal to 1. A reminder, for P equals 1, this map norm sub 1 is indeed a norm. Therefore, L1 is a normed vector space consisting of random variables that have a bounded absolute mean IEE. Expectation of absolute x is finite. Some more reminders about LP spaces. Norm x sub infinity is defined as the essential supremum of absolute x of omega over omega in omega. L infinity is then the normed vector space of essentially bounded random variables. The function norm sub p is indeed a norm for all p in the open interval 1. Infinity as well, this requires Minkowski's inequality for the triangle inequality part. Hence, LP is a normed vector space of random variables that have a bounded norm sub p. In particular, the L2 space consists of random variables with a bounded second moment, or more precisely, E of x squared, expectation of x squared is finite. If expectation of absolute x to the n is finite for some natural number n, then expectation of absolute x to the k is finite for all k in 1 to n, i.e. for k from 1 to n. This is because absolute x to the k can be written as absolute x to the k times indicator, that absolute x lesser than or equal to 1 plus absolute x to the k times indicator, that absolute x greater than 1. This is less than or equal to 1 plus absolute x to the n, assuming k lesser than or equal to n. This implies that Ln is a subset of Lk for all k in 1 to n. More generally, Lq is a subset of Lp for any real numbers such that 1 is less than or equal to p, which is less than or equal to q. Now let's turn to central moments. Consider an example, shifted polynomial functions. For any k in n, we define functions hk from r to r such that hk maps x to x minus m1 to the k, where m1 is the first moment, the mean. Then hk can be seen as gk of x minus m1, which is gk composed with f, where f from r to r is defined as f of x equals x minus m1. Since gk of x to the k and f of x minus m1 are both measurable functions, their composition hk is also measurable. This allows us to define central moments. Let x be a random variable from omega to r, defined on omega, script f, p with a finite first moment m1. We define the kth central moment of the random variable x as sigma k, which is e of h k of x, or e of x minus m1 to the k expectation of x minus m1 to the k. The second central moment, sigma 2, which is expectation of x minus m1 squared, is called the variance of the random variable and is often denoted by sigma squared. We have a lemma regarding central moments. The first central moment, sigma 1, which is expectation of x minus m1, is always 0. The variance sigma squared, which is expectation of x minus m1 squared, for a random variable x is always non-negative. It is equal to 0 if and only if x is a constant equal to m1, almost surely. From this, it also follows that m2, the second moment, is greater than or equal to m1 squared, the mean squared, with equality holding if and only if x is a constant. Let's prove this. h1 of x is x minus m1 and h2 of x is x minus m1 squared. Both are random variables. Sigma 1 is expectation of h1 of x, which is expectation of x minus m1. Since m1 is expectation x, this is 0. Since x minus m1 squared is always non-negative, its expectation, sigma 2, must be greater than or equal to 0. Expanding sigma squared, expectation of x squared minus 2 1 x plus m 1 squared equals expectation of x squared minus 2 1 expectation of x plus m1 squared. This is m2 minus 2m1 times m1 plus m1 squared, which simplifies to m2 minus m1 squared. So m2 minus m1 squared is greater than or equal to 0. A quick reminder, if the second moment is finite, then the first moment must also be finite. That is, L2 is a subset of L1. Now let's look at some important inequalities. First, Markov's inequality. Let x be a random variable from omega to r defined on omega, script f, p. Then for any monotonically non-decreasing function f from r to r plus non-negative values, we have the probability p that x is greater than or equal to epsilon is less than or equal to expectation of f of x divided by f of epsilon, assuming f of epsilon greater than 0. For the proof, any monotonically non-decreasing function f from r to r plus is Borel measurable. Hence, f of x is a random variable for any random variable x. Therefore, f of x can be written as f of x times indicator of x greater than or equal to epsilon plus f of x times indicator of x lesser than epsilon. Since f is non-decreasing and takes non-negative values, this is greater than or equal to f of epsilon times the indicator that x is greater than or equal to epsilon. The result then follows by taking expectations on both sides and using the monotonicity of expectation. A direct corollary of Markov's inequality is what's often just called Markov's inequality. Let x be a non-negative random variable, then the probability p that x is greater than or equal to epsilon is less than or equal to expectation of x divided by epsilon for all epsilon greater than 0. This uses fx equals x, which is non-decreasing for non-negative x. Another important corollary is Chebyshev's inequality. Let x be a random variable with a finite mean m1 and a finite variance sigma squared, which is sigma 2. Then the probability p that the absolute value of x minus m1 is greater than or equal to epsilon is less than or equal to sigma 2 divided by epsilon squared for all epsilon greater than 0. To prove this, we apply Markov's inequality to the non-negative random variable y equals absolute x minus m1 and use the increasing function f of x equals x squared for x greater than or equal to 0. So p of absolute of x minus m1 greater than or equal to epsilon equals p of absolute x minus m1 to the power 2 greater than or equal to epsilon to the power 2 lesser than or equal to e of absolute x minus m1 to the power 2 by epsilon to the power 2 equals sigma 2 by epsilon to the power 2. And a third corollary, Chernoff's bound. Let x be a random variable such that expectation of e to the theta x is finite for some theta greater than 0. Then the probability p that x is greater than or equal to epsilon is less than or equal to e to the minus theta epsilon times expectation of e to the theta x for all epsilon greater than 0. The proof involves applying Markov's inequality to the random variable x using the increasing function f of x equals e to the theta x which is positive for theta greater than 0. So P of x greater than or equal to epsilon equals P of e to the power theta, x greater than or equal to e to the power theta, epsilon lesser than or equal to e of e to the power theta, x by e to the power theta epsilon.
Next, let's define a convex function. A real valued function f from R to R is convex if for all x, y in R and for all theta in the closed interval 0.1 we have f of theta x plus 1 minus theta I is less than or equal to theta f of x plus 1 minus theta f of y. Geometrically, the line segment connecting any 2 points on the graph of f lies above or on the graph.
This leads to Jensen's inequality. For any convex function f from R to R and any random variable x whose expectation exists, we have f of expectation x is less than or equal to expectation of f of x. Let's sketch the proof of Jensen's inequality. For simple random variables, x from omega to a finite set script x, we can show this by induction on the cardinality of the alphabet script x. The inequality is trivially true if the cardinality of script x is 1x is constant. Assume the inductive hypothesis holds if the cardinality of script x is n. Now let x take values in script x where the cardinality of script x is n plus 1. Let script x be x1 up to xn plus 1 with pi being the probability p that x equals xi. The collection pj divided by 1 minus p1 for j greater than or equal to 2 forms a probability mass function for some random variable y that takes values in script y equals x2 so on till xn plus 1 which has cardinality n. By our inductive hypothesis, f of the sum from I equals 2 to n plus 1 of pi by 1 minus p 1 times xi, which is f of expectation y, is less than or equal to expectation of f of y, which is the sum from I equals 2 to n plus 1 of pi by 1 minus p 1 times f of xi. Now, applying the definition of convexity of f with data equals p1x equals x1 and y equals the sum from I equals 2 to n plus 1 of pi by 1 minus p1 times xi, which is e of y, we get f of expectation x, which is f of p1 x1 plus 1 minus p1 times sum I equals 2 to n plus 1 pi by 1 minus p1 xi is less than or equal to p1f of x1 plus 1 minus p1 times f of sum I equals 2 to n plus 1 pi by 1 minus p1 xi. From the inductive step, the second term 1 minus p1 times f of e of y is less than or equal to 1 minus p1 times e of fy, which is 1 minus p1. Sum of pi by 1 minus p1 times fxi equals sum I equals 2 to n plus 1 pi times fxi. So the right hand side is less than or equal to p 1 times fx1 plus sum I equals 2 to n plus 1 pi fxi, which is expectation of f of x. The result follows. This can then be extended from simple random variables to general random variables by approximation. Finally, returning to LP spaces, we have a theorem regarding their relationship. For any real number such that 1 is less than or equal to p, which is less than or equal to q, which is less than infinity, we have that LQ is a subset of LP. Let's prove this. Let 1 lesser than or equal to p lesser than or equal to q lesser than infinity. Consider a convex function g from r plus to r plus defined by g of x equals x raised to the power q over p. Since q by p greater than or equal to 1, this function is convex for x greater than or equal to 0. It follows that g of absolute x to the p is absolute x to the p to the q by p, which equals absolute x to the q. Now, applying Jensen's inequality, norm x sub p all raised to the q is e of absolute x to the p to the 1 by p to the q, which is e of absolute x to the p to the q by p. This is g of e of absolute x to the p. By Jensen's, this is less than or equal to e of g of absolute x to the p. Expectation of g of absolute x to the p. And e of g of absolute x to the p is e of absolute x to the q. Expectation of absolute x to the q, which is norm x sub q, all raised to the q. So norm x sub p to the q is less than or equal to norm x sub q to the q. Taking the qth root, since norms are non-negative, we get norm x sub p is less than or equal to norm x sub q. This means if norm x sub q is finite, so x is in LQ, then norm x sub p must also be finite, so x is in LP. Thus LQ is a subset of LP. This concludes our lecture on moments, LP spaces, and important inequalities.